Okay, remember on the Taylor and Maclaurin series, whenever they give us a string of terms like that, and if I see a derivative notation in the problem, which is what I see right here, I'm meant to just multiply by the power, decrease the power by 1, and take the derivative of those terms. If I see an integral notation somewhere in the problem, I'm just meant to integrate those two things. So I'll go like x squared over 2, x to the fourth over 4, and then integrate those two terms right there. That's what you're meant to do, even if the notation looks complicated and stuff like that. Now, part A is like our power series video. You're supposed to find the interval of convergence here. So we're going to do the ratio test. It even tells you to use the ratio test, but we know we're going to use the ratio test here. And we're going to do a limit as n approaches infinity. You're going to replace those n's with n plus 1s. You're going to divide it by the original. So there's your a sub n plus 1. You're going to divide it by the original, which means you multiply by the reciprocal. And remember, to get this ratio test to converge, we need that to be less than 1. And then I rewrote that as x to the 2n times x to the first, x to the 2n times x to the third. The x to the 2n's canceled. X cubed over x to the first was x squared. The other stuff just carried down. And then at this point, you pull out any of your non-n terms outside with the absolute value bars, but I don't really need the absolute value bars here because absolute value bars are always positive. X squared is also always positive. So I don't need to worry about the bars so much on this one. So I just get the x squared. That limit answer, the degrees are the same. It's the leading coefficients. That's equal to 1. And then right here, instead of like making up your own stuff, to remember, this is a nonlinear inequality. So let me get the rest of this on the screen here. Nonlinear inequality is when you move everything to one side, find the zeros of this thing and do your number line thing. So put the 1 and -1 on the number line, do 0 for a test point, 0 plus 1 is positive, 0 minus 1 is negative, positive times negative is a negative number. You don't see any even exponents there, so no double roots, so the signs are going to alternate, and you're picking out the interval where it's less than 0, that's in between the -1 and the positive ones. And remember, whenever we do that interval convergence and ratio test and you get an interval like that, you got to check the endpoints, because when the ratio test is equal to 1, then that test is inconclusive. So you got to do a test, by yourself there. Now, the x equals -1 looks a little bit trickier. All I'm going to do is take this -1 and plug it in for that x into the original problem. So that's going to carry down, that's going to carry down, and I have -1 to this 2n plus 1. Now, sometimes those are an alternating series, sometimes they're not. Like if I get -1 to the 2n, that's always positive, and it's not an alternating series. But here, I'm not sure, you might have a slightly different way of thinking about it, but I just added up those exponents. So n plus 2n gave me the 3n, and the plus 1 carried down. And I just thought, okay, if I plugged in 0, that'd be -1 to the first, which is a negative number. And if I plugged in 1, that'd be -1 to the fourth, which is a positive number. So the signs are going to alternate. So I just kind of turned it into something more familiar. I didn't need to do that step, but I just plugged in 0, 1, and 2, and I saw that the signs were alternating. So I just kind of turned it into something more familiar, like we're used to with the alternating series test. But that is an alternating series, and that converges. You don't need to show all that work, but that's a convergent alternating series. Now, if you wanted to show your whole alternating series test, you can do the limit as n approaches infinity of the 1 over 2n plus 3 is equal to 0, and then the a sub n plus 1, so you'll go 1 over 2 times that n plus 1, so that'd be 2n plus 2 plus 3, so that'd be 1 over 2n plus 5 is less than the 1 over 2n plus 3, and that's true since that 2n plus 5 is greater than 2n plus 3, but you don't have to show that much work there, right? So just kind of do that alternating series test in your head and get that converges. And when I plugged in x equals 1, it was easier. X equals 1 right there is just 1 to a power. And then so that's just going to be 1. And then that -1 to the end just carries down. And then that's a straight alternating series. Converges the same way. So since both of the endpoints converge, that means we got to put bars under there. We got to turn those parentheses in the bracket. I think we had one like that in the past where both of them diverged, and you still got to check those endpoints, because even if they both diverge and you just get lucky and get the right answer because you forgot to check them, they'll have on that rubric, if you didn't check the endpoints like you're supposed to, you won't get full credit right there. So show them, you're going to get so many points for this, and then checking your endpoints, you'll get points for the rest of that problem right there. But it's possible they might both converge, might both diverge. A lot of times one might do, converge, one might diverge, and you just adjust your parentheses and your brackets off of there. If I got diverge for either of those, then I just leave it up parentheses. Okay, letter B looks crazy intimidating, But here's what I wrote a smiley face. Hey, this is music to my ears. When I see that phrase, alternating series whose terms decrease in absolute value to zero, or if you notice that your series alternate sign and then you got 1/3, 1/5, 1/7, where those just keep getting smaller and smaller, that's wonderful news, because when they ask me to find the error of something, that's just going to be the next term in our sequence right there. Now let's kind of look through this notation. So why we're doing the error, I don't see the word error in this problem like we normally do, but it says the approximation for that using the first two terms of that is that, right? And then show that the approximation differs. So anytime you're talking about the difference between the true value and the approximated value, or how much the approximation differs from the actual value of the actual curve solution, you know, that's an error. What's the difference between the true value and the approximated answer right there? And alternating series terms decrease not specified to zero, you're going to do the next term. You ain't got to worry about the Lagrange error bound or any of that weird stuff. Just go to the next term. So since it told us it used the first two terms, that means they used these two guys right here. So the next term we didn't use was the x to the 5th over 7. Now, if I had a negative right there, I'm just going to do the absolute value bar of that. You just want to know what that number part is there. So it's always the absolute value of that next term. And so I started with that x to the 5th over 7, and I had that x equals 1/2 all throughout that problem. Just plug the 1/2 in place for the x right there. You get 1 over 32 times 7. I kind of did that in my head, but then I just double checked it using the old school multiplication. Got this 1 over 224, and they just said show that that is less than that 1 over 200 right there. So that's all you got to worry about. All right. So this is at least the third time we've seen something like that where we know what to do with that in the future. We'd be perfect with that stuff. All right. And then we said letter C was that write the first three non-zero terms in the general term of the Maclaurin series for G prime of X. So this is a Maclaurin series for G. And they gave us a few terms right there. And now they want us to get one for G prime. And like we said at the beginning, they're just meaning for us to take the derivative of each one of those terms right there. Now, and so like the derivative of like 1/3 x was just 1/3, right? The derivative of this, I'm just gonna get 3x squared over 5. So I got that. And then I'm just gonna multiply by the power, decrease power 1. So we're gonna get 5x to the 4th over 7. Now, that's easy to just do the derivative of those few terms and get those few terms right there. Sometimes it asks for this general term, sometimes it doesn't. The long way to get this general term is try to study the pattern. See how you got odd numbers right here, 1, 3, 5. So that could be like a 2n plus 1 or a 2n minus 1. So if you start with that 2n plus 1, and then you have to notice that these are also odd numbers, but they're 2 bigger than that one, that's that 2n plus 3, the 3 is 2 bigger than that 1 right there. And it alternates signs, so I could throw that alternating symbol notation in there. I don't like that technique. Sometimes I have to see the even and odd stuff and do the 2n and 2n plus 1. It's so much easier than that. And I didn't know that when I first started doing all my teaching, but it's so much easier to get this, and you don't have to do any guesswork, because sometimes my brain doesn't see those patterns. And so look how simple this is, right? I told you, this is your G, this is your G prime. It's easy to take the derivative of those to get those. What you can do to get the general term for G prime is this is the general term for G. You could take the derivative of that, okay? The n's are just numbers. The x is your only variable. So let's actually do that from scratch. I think that'd be beneficial. Let's do an easier problem. If I give you x to the 10th over 3, we know that's the same thing as 1/3 x to the 10th, right? And so when you take the derivative, you're just going to multiply by the power. You're going to go 10, and then the 3 stays there, right? It's just 10 times the 1/3. So it's going to be 10/3, and then you're going to decrease that power by 1. That's all I'm going to do right here. It just looks worse than it actually is because it has all these letters in there, but the n's are just numbers. This is just x to a power, and this is just some number on the bottom. So technically you could rewrite this as 1 over 2n plus 3. That's like a 1/3 up there. X to the 2n plus 1. That's like our x to the 10th up there. And then when you take this derivative, you're going to multiply by the power. So you're going to take the 2, just like I took the 10, times it by the 1/3. I got 10 over 3. I'm going to take the 2n plus 1 times it by this 1 over 2n plus 3. And that's just going to give me 2n plus 1 over 2n plus 3. I can't really do anything with that. So that's just like your 10/3 right there that carries down. And then you're going to decrease that power by 1. Well, if you take 2n plus 1 and you subtract 1 from that, those ones cancel out, and you get that 2n, and then notice that this right here is what I got down from my work right here, that main part of it, right? That 2n plus 1 over 2n plus 3 x to the 2n. And then the alternating series notation will always just stay the same and carry down. So see how that was -1 to the n? This is also just going to be the same thing, -1 to the n, because the signs are going to alternate as well. Because if you got a positive or a negative, you're going to just, those are just going to carry down the same exact way right there. So even if I had to integrate that thing, let's just do that for fun. If I had to integrate this thing, if this was the 2n plus 1 over 2n plus 3, and let's say I had to do an integral of that, I could integrate that thing. That's really like 1 over 2n plus 3 times the integral of x to the 2n plus 1, right? And then so when I integrate this, I would add 1 to that exponent. So that would give me 2n plus 2. But then I would divide it by that same exponent. So I would divide it by the 2n plus 2, and then that 2n plus 3 would kind of carry down. So that one looks funky just because I just made that up at the top of my head there. But if you ever have to do a derivative or an integral of that general term, you can just differentiate or integrate that general term that they gave us, and then everybody's happy right there, right? So again, try that stuff all on your own there, and then you can merge. We've done several of these Taylor problems already now, where you kind of merge like 4 or 5 of them together and just kind of study those all by themselves. I think that'll be helpful there. Sugar.